So I mentioned previously that there's various spaces of matrices that provide good examples for various phenomena in topology. So we're going to explore that a little bit here. So I'm going to be concentrating on the space O2. So let's just recall the definition of that. So that's a set of 2 by 2 matrices, 2 by 2 real matrices, with the property that A transpose A is the identity matrix. Okay, so let's spell that out. Matrices A, B, C, D, where A, B, C, D are all real. The property that we take the transpose, so the transpose is going to be A, C, B, D times the original matrix A, B, C, D. Has to be equal to the identity. And if we just carry out this product, right, so here you get top left, you're going to get A squared plus C squared has got to be equal to 1. And then the next entry, you get AB plus CD has got to be equal to 0. The next entry, you get this BA plus DC has got to be equal to 0, but BA plus DC, that's just the same as that. So we just get the same equation again, we'll ignore that one. Then you get B squared plus D squared has got to be equal to 1. And we could rewrite this in a slightly different way. So this is saying that AC is a unit vector. This is saying that BD is a unit vector. This is saying that AC and BD are perpendicular to each other. And so it's AC and BD are orthogonal unit vectors. Okay, so that's how we can unwind the definition of O2. Okay, so now I'm going to claim as a homeomorphism F from S1 cross S0 to this space O2. Given by F of X, Y, Z. X, Y minus Y, Z, X, Z. And F inverse the matrix A, B, C, D is A, C, AD minus BC. Okay, so so let's just recall about what is this S1 cross S0. I mean, S1 cross S0, right? So that's an element of S1. S1, remember, is just the unit circle, so that's just a pair XY with X squared plus Y squared equal to 1. And then and then Z is supposed to be an element of S0. But S0 is the unit vectors in the real line. That's just plus or minus 1. So Z has got to be plus or minus 1. And so that's what this space S1 cross S0 is. And so this is basically the union of two circles. The circle crossed with plus 1, the circle crossed with minus 1. And so that's claiming that this is a homeomorphism. Well, the first thing is to check that this formula F really does define a function like that. So in this thing here, X, Y minus Y, Z, X, Z, we have well, X squared plus Y squared is certainly equal to 1. That's part of the definition of this S1 cross S0. And then we look at the other one, minus YZ squared plus XZ squared. Well, Z squared, Z is plus minus 1, so Z squared is 1. Minus Z squared is also 1. So this is just Y squared plus X squared. That's, of course, equal to 1 as well. And X times minus YZ plus Y times xz, well, that just cancels out, you just get 0. So we're seeing from this that f really is giving this formula for f. This really is giving us a map S1 cross S0 to O2. Okay, so that's our first step. We've at least got one of the maps that we need. So now let's try and make the map in the other direction. So if we've got this ABCD, if that's in O2, well then firstly, we've already seen that AC is a unit vector. We should also notice that A transpose A is the identity, and det A transpose and det A are both equal to AD minus BC. Det A squared is det A transpose A. That's the determinant of the identity, which is 1. So from this we see that AD minus BC is plus or minus 1. So that means if we look at this formula G of A, B, C, D equals A, C, AD minus BC, and this formula gives a map from O2 to S1 cross S0. Because we know that we know that AC is a unit vector, so that gives you a point in S1, and AD minus BC, we've just shown that's equal to plus or minus 1, so we're getting a point in S0. So the next thing we need to check is that the composites are right. So we take the determinant of this this thing that's produced by F. Okay, so then if we take this, that's going to be x squared z plus y squared z. Okay, just expanding the term in the obvious way. But x squared plus y squared is equal to 1, so that's just equal to z. Using this, we see that if we take g of f of x, y, z, you just get your x, y, z back. Okay, so that's one of the composites is the relevant identity map, and we just need to check it the other way around as well. Yeah. So now if we are given some A, B, C, D, and O2, then if we look at f of g of that, well, you get a matrix. So we know the matrix we get is like A. If you just look at the formula, you get A, C, and then here And then here you're going to get minus ZC ZA. Where Z is AD minus BC. But we know this lies in O2. That means that the second column is perpendicular, is a unit vector perpendicular to AC. And therefore it's got to be equal to plus or minus BD, right? You know that BD from the original matrix, BD has got to be it's got to be a unit vector that's perpendicular to AC, and then this thing here is also a unit vector that's perpendicular to AC, and there are only two possibilities, right? If we draw the kind of picture, you've got your AC is here, and then you've only got two possibilities: AC here, and then maybe BD is here, and then minus BD would be pointing down there. There's only two possibilities. And then you just take determinants. To see that you must get it's got to be equal to BD. And that proves that the composite the other way around is the identity as well. And so we have indeed got, and also it's clear that these map F and G are both continuous because we've just got polynomial entries. So we've got continuous map both ways and they're inverse to each other. So we've got a homeomorphism.